to the next class of data communication network. In the last class, we were talking about cyclic redundancy check, where the given data word is represented in form of ones and zeros, and we have a divisor which we will try to divide the given code word, and we try to determine the remainder. The remainder will represent the redundant bits to be added to the data word so that it can be converted to code word. And again at the receiver, the received code word will be divided with the divisor used at the transmitter, and if the syndrome, which is the remainder generated, is 0, it indicates there is no error present in the data received. If the value of syndrome is not equal to 0, then the value of the remainder generated would be indicating the position at which the error has been generated. Now coming to today's topic, here in cyclic redundancy check, along with representing data in form of ones and zeros, we have an other option where we try to represent the data word and the code word in form of polynomials instead of a series of zeros and ones. Let us take a simple example to understand this phenomenon. When your code word to be transmitted is represented as 1000011. So in terms of polynomial, we start with x power 0 for the initial variable a0, and we'll try to increase the power of x. Now x power 0, the a0 value is 1, x power 1, a1 value is 1, for a2, a3, a4, a5, which are representing powers of x power 3, 4, 5 or 0, and again a6, which is the coefficient of x power 6, is 1. So the total expression we have is 1 into x power 6 plus 1 into x power 1 plus 1 into x power 0, and simply it can be referred as x power 6 plus x plus 1. So this is the code word which we are trying to transmit, and that has been represented in form of polynomial. Right. Here the data word to be transmitted is represented as a polynomial called x power 6 plus x cube, and the divisor which we are using is x cube plus x plus 1. So let me for make you comfortable, let me try to represent it in terms of ones and zeros. 1 0 1 1. So this will be indicated with x cube plus x plus 1, and this particular dividend is nothing but x power 6, x power 5 is 0, x power 4 is 0, x cube is 1, and remain x square, x, and x power 0 is 0. So this is the code word to be transmitted, and this is the divisor which we are trying to use. Now let's implement this cyclic redundancy check process in terms of polynomials. So the divisor is x cube plus x plus 1, and the dividend is x power 6 plus x cube. Now once we start dividing it, again similar to the modulo 2 division we are using here, and x power 6 divided by x cube. So the minimum coefficient we get is x cube. So first multiply the total divisor with x cube, then we are going to get x power 6 plus x into x cube is x power 4, and 1 into x cube is x cube. So x power 6 minus x power 6 is 0, then it is modulo 2 subtraction, so it is just x power 4, and x cube minus x cube becomes 0. So we are left out with x power 4. The next coefficient value to divide with x cube is x. So x cube into x is x power 4 plus x into x square plus 1 into x. So after subtracting x power 4 from x power 4, we are left out with a remainder called x square plus x, which is referred as the redundant bits during the transmission. So initially we started making an assumption that the redundant bits are zeros. Now we have to replace the redundant bit values with x square plus x. So the total code word which we are going to transmit is x power 6 plus x cube plus x square plus x. The divisor in a cyclic code is normally called as generator polynomial or simply the generator. So we had used three variables there: divisor, dividend and quotient. So the divisor which is used in the cyclic redundancy check will be referred as a generator polynomial or simply a generator. Now, when you are trying to forward this transmitted code word to the receiver and divide again that particular received code word with the divisor that is used at the transmitter. If you get syndrome, which is nothing but the remainder, is not equal to 0, then it indicates one of the variable got affected, and that is the reason why syndrome was not equal to 0 and an error has been generated. But in case the received code word is divided by the syndrome by the divisor and the syndrome value is 0, it means two of the scenarios. One is whatever the data that has been transmitted was received perfectly, and second one is the error that has been generated also was being failed to be detected by the divisor, because might be the reminder that has been generated will be divisible by the divisor, and so we get 0. So errors that are divisible by g of x, that is whatever the errors that have been generated during the transmission, they are divisible by the divisor g of x, then they cannot be identified by the cyclic redundancy check. So the most important applications of cyclic redundancy check represented in polynomials for different applications are: if your highest degree of cyclic redundancy check is 8, the polynomial used is x power 8 plus x square plus x plus 1, and this is used in an application called asynchronous transfer mode header. If the highest degree used in cyclic redundancy check is 10, it is we start with x power 10 plus x power 9 plus x power 5 plus x power 4 plus x square plus 1. So this polynomial is used in an application called ATM adaptation layer. Then cyclic redundancy check 16 with the highest degree of 16. This will be used in application called HDLC, which we are going to discuss in this topic after this topic. And the expression for that is x power 16 plus x power 12 plus x power 5 plus 1. And if the highest degree used in cyclic redundancy check is 32, so we start with x power 32 followed by x power 26 plus x power 23 plus x power 22 and so on. This expression will be referred for an application called LAMS. So generally you people will be expressed with application name and what is the highest degree. In rare cases you might be asked even the expression of polynomial for the concerned application. Now, having understood the way a cyclic redundancy check is implemented, how we are implementing the division of the given dividend with divisor, determining the remainder, and replacing the redundant bits from zeros to remainder. The combination of data word with remainder is called code word, which is transmitted to the receiver. At the receiver, this will be forwarded to a checker device where the received code word is divided with divisor used at the transmitter, and if the syndrome, which is the remainder generated, is not equal to 0, error is generated. If it is equal to 0, either no error is generated, or even if the error is generated, that is divisible by the divisor polynomial g of x. Now, what are the advantages for using cyclic codes? The first one is the cyclic codes have very good performance in detecting single, odd number and burst errors. So in case of even errors, it may not be working good. And next, it can be easily implemented in both hardware and softwares, and it can be used in many networks. So these are the few of the advantages which cyclic redundancy check possesses, because of which it has been one of the very popular techniques in different networks. I hope we are clear with cyclic codes and cyclic redundancy. Cyclic codes, if you are cyclically shifting the code word, the resultant should generate another valid code word. So far we have discussed different types of error detection techniques like parity check, two-dimensional parity check, Hamming distance, minimum Hamming distance, Hamming code, cyclic redundancy check. And now we'll discuss the last type of error detection technique called as checksum. So what checksum is one of the widely used protocol, although this has been not used at the data link layer. So we need to understand this because in most of the protocols you will be finding checksum as the error detection and correction technique implemented. So let us have an understanding of the checksum method. So far we have discussed different types of error detection techniques like parity check, two-dimensional parity check, Hamming code, and cyclic redundancy check. The last technique of error detection that we would like to discuss is called checksum. First, let us try to understand what do you mean by checksum. Suppose I have to transmit 5 different numbers represented in 4 bits to the destination. So here, in addition to transmitting those 5 numbers, we are going to calculate the sum of those 5 numbers, and along with those 5 numbers we are also going to transmit the sum of those 5 numbers. At the receiver, once again we'll try to add those 5 numbers which we have transmitted, and we'll check if that sum generated is same as the sum that is being generated at the transmitter. The two sums are same, then the receiver assumes that there is no error and accepts those 5 numbers. The two sums are different, then it will indicate some error has been generated. Let us try to understand this with the example which is stated. For instance, I am going to transmit 5 numbers called 7, 11, 12, 0 and 6. So this 5 numbers are represented in 4 bits like 0, 1, 1, 1, then 11, 1, 0, 1, 1, then 12, 1, 1, 0, 0, 0, 0, 0, 0 and 0 and 6 indicated as 0, 1, 1, 0. We people have learned in our previous subjects like digital electronics and digital communication how to convert a given numbers into binary, at the same time how to convert binary numbers to the other forms of numbers. Okay, so here we are converting our given numbers into 4-bit binaries, and we are trying to calculate the sum of those 5 numbers. So the 5 numbers transmitted were 7, 11, 12, 0 and 6. The sum of these 5 numbers is 7, 11 plus 7, 18, 18 plus 12, 30, 30 plus 6, 36. So along with the 5 numbers, we are going to transmit the sum of these 5 numbers. Once the numbers are received at the receiver, for instance, there is no error. So all numbers are received as it is. So at the receiver, I am receiving 7, 11, 12, 0 and 6. Same as what we have received, transmitted. So when there is no error in the transmission and we get the bits and the number as it is, here the sum again is calculated, which is 36, and both the sums, the transmitter and receiver, are matching with each other. We say that there is no error generated during transmission. For instance, for a small factor, one of the bit got affected. Here instead of 1011, we got an error and it has been converted as 1010. Now 1010 is nothing but 10. Now when it becomes 10, the sum of the numbers here is 17 plus 12, 29 plus 6, 35. So instead of 36, we get sum as 35, which is not equal to the sum that has been transmitted at the transmitter. So we will indicate an error has been generated. This is one way of implementing a checksum. Now there is an alternative to implement the checksum. The other method of implementing checksum, instead of just transmitting the sum of the numbers along with the 5 numbers, what we are trying to do is we are trying to send the negative or complement of the sum. So in previous slide we could determine the sum of those 5 numbers as 36. So here instead of sending the sum 36, we are trying to send the negative of the sum, which is minus 36, and this minus 36 is called checksum. Now once this 6 numbers are received at the receiver, that is the 5 numbers transmitted along with the checksum value, we are again trying to calculate the sum of all the numbers including checksum. 7, 11, 12, 0, 6 and minus 36. Now in case if there is no difference in the any of the bits that have been transmitted and all the numbers are transmitted without error, what happens is the sum of all these numbers, 7 plus 11 18 plus 12 30, 30 plus 6 36, minus 36, that becomes 0. So if you are adding all the numbers including the checksum at the receiver, and if the sum is equal to 0, it means that no error has been generated. If in case if it is not equal to 0, there is an error generated during the transmission. Now let us look at this particular problem implementation. So here, as we shown earlier, we are going to have 0, 1, 1, 1, 1, 0, 1, 1. 12 is represented as 1, 1, 0, 0. 0 is indicated as 0, 0, 0, 0, and 6 is indicated as 0, 1, 1, 0. Initially what we do is we make the assumption of the sum as 0. And now what is the total sum generated? So assuming the checksum value initially as 0, the sum of all the numbers is 7 plus 11 12, 18, 18 plus 12 30, 36. So sum becomes 36. And 36 when represented in form of binary, it is represented as 36 in binary is represented as 32, 16, 8, 4, 2 and 1. So we are getting a 6-bit binary to represent 36. But all the above values are represented in 4 bits. So what we do is the first 2 bits of this sum will be wrapped, that is indicated in this. The first 2 bits of this will be wrapped. So the total sum was 36, and now the wrapped sum, so 1 and 0 will be moved to the next, and we are trying to calculate the modulo 2 addition. So that is 0 plus 0 0, 0 plus 1 1, 1 plus 0 is 1, 0 plus 0 is 0. Now this is called wrapped sum. So when you are moving those 1 0 to the bottom and trying to generate, so the wrapped sum of this is 6. And what is expected is not just sending the wrapped sum, but we have to send the complement of the wrapped sum. So this 0 1 1 0 complement is nothing but replace zeros with ones and ones with zeros. We are going to get 1 0 0 1, which is equal to 9. So the checksum that is going to be transmitted along with the 5 numbers are 7, 11, 12, 0, 6 is 9. Now this is forwarded to the receiver, and as explained in the previous, along with the 5 4-bit numbers, you're also going to add the checksum value. So when you try to add all these numbers including the checksum, what is the value? 7 plus 11 is 18, 18 plus 12 is 30, 30 plus 6 36, plus 9 is 45. Now 45 in terms of 4-bit binary, 32, 16, 8, 4, 2. So it is 101101, and we have to wrap the first two bits in the wrapped sum generated at the receiver is 45, which is now converted, make it wrap, and now you will find the sum converted as 1 plus 0 is 1, 0 plus 1 is 1, 1, 1. So after wrapping the generated sum, resultant is 1111, which is nothing but 15. So 15, when you take its complement, all ones become 0. So final resultant is 0. So after calculating the sum, wrapping the sum, and then finding its complement, if the resultant is 0, then it indicates the calculated sum is correct. If this value is not equal to 0, it indicates there is some error generated during the transmission. What are things that we are actually trying to do at the sender? Just putting it in form of chips. First, we are dividing the message into 16-bit words, or you can set it as saying that 5 4-bit numbers kind. Then initially the value of checksum is assigned to be 0. All the words including the checksum are added using one's complement addition. That is what we have discussed. Wrapping the sum and then taking the complement. And then after implementing the complement addition, the sum is complemented and it becomes the checksum. In the previous case also, we have first tried to determine the wrapped sum. Then we have the complement of that wrapped sum and it referred as checksum. So the checksum is also sent along with the 5 numbers which we have to transmit. So first divide into numbers into 4 4-bit representations we have done. Then we try to determine, initially we have set the checksum as 0. Then we determine the total sum. Then we wrapped the sum into 4 bits, and later we took the complement of those wrapped sum. Now at the receiver, here also we'll try to divide the message into the words. Then all words are added using one's complement addition. Once the addition value is generated, we'll again implement the wrap sum of it, and then the sum is complemented, and the new complemented sum will be called as the new checksum. If the value of this new checksum is 0, it means the message is correct without any error. And if the value of this new checksum is not equal to 0, it indicates some error has been generated during the transmission. This is what all about checksum and how it is implemented in communication. Remember, checksum is one of the very important error detection techniques used in the transmission. The next topic which we are going to talk is called framing, which is one more important function of the performed by the data link layer. We know that data link layer lies between network layer and physical layer. So what data link layer does is it receives the data from the network layer and convert that particular data into a manageable units called frames. The process of converting the data from network layer, which is in form of packets, into frames is referred as framing. So what we actually try to do is, in framing, we are receiving the data from the network layer, add header and trailer to it, and convert it into frames. So the header part of the framing will be consisting of source address and the destination address. And the trailer part of this consists of the error detection correction data. So basically, based on the size of the frames, we categorize the frames into two types. The first type of frame is fixed size frame, where all the frames that are generated will be having a uniform size, and there is no need of defining any boundaries between two frames. For instance, I will divide every data into 4 bits. For instance, I have a data 9 and I have another number 6. 9 to represent in binary, I require 4 bits 1 0 0 1. But if I want to represent 6 in binary, I just require 3 bits, which is 1 1 0. Now if I am representing the two different numbers with two different size of bit numbers, we refer it variable size. But to make it a fixed size, I also represent 6 also in terms of 4 bits by putting the fourth bit here as 0. So fixed size frame means all the frames which are used will be having a fixed size, and so there is no need to define any boundary between the frame. And here the major application where we try to use the fixed frames are called frames in asynchronous transfer mode wide area networks, and these are also called as sets. Now in the other scenario where you need not have this requirement, for instance 6, and next if I have value like 3 or 3, I just require 2 bits to represent 1 1. But if I talk about fixed size, I have to represent 3 also as 0 0 1 1. But if it is variable size, I can just represent it as 1 1. So this is the difference between fixed size frames and variable size frames. So here also, here frames can have different sizes, that will be referred as variable size frames. And here to separate two frames, we need to define a boundary to indicate the difference between two consecutive frames. Generally, this type of variable frame sizes are used in local area networks. So framing means to convert the data received from the network layer, which is in form of datagrams or packets, to the frames by adding header and trailer. Header consists of source and destination address, trailer consists of error detection and correction information. The frames which are formed is classified into two types. If all the frames generated are of fixed size, then we call it as fixed size frames. If the frames formed are of different size, we call it as variable size. For fixed size, no boundary is required. For variable size, we require a boundary to separate two adjacent frames. Fixed size frame example we have is ATM vans, what are the frames we are used, whereas variable size frames, where example is the frames used in the local area networks. So to handle the variable size frames, we have two different approaches. The first one is called character oriented approach, and the second one is called as bit oriented approach. So what do you mean by character oriented approach, and what do you mean by bit oriented approach, and how to discriminate these two approaches? Right. Let us first start with character oriented approach. When you are talking about variable size frame in character oriented approach, so in character oriented approach, every data to be transmitted is represented as 8-bit characters. For this, we are using systems such as ASCII. For instance, I've been talking like I want to send a data called 20. Data 20 has to be transmitted. So I'm going to represent 20 in 8 bits, like 256. Sorry, what this is 128, 64, 32 is 0, 16 is 0. Sorry, 16 we have it is 1. So 20 in binary is nothing but 1, 8 is 0, 4 is 1, 2 is 0, 1 is 0. So all the data that has to be transmitted is represented in 8-bit characteristics. Okay, so the header which we have been talking about consists of the source and the destination address, while the trailer part consists of the error detection and correction bits. And here, even the error detection and correction bits are also represented in 8-bit form. Okay, now just as we discussed in the previous slide, we are going to receive the data from the upper layer. Here, the data will be in form of 8-bit characters, that is nothing but bytes, and the data will be accompanied with header and trailer, which consists of source and destination information and some control information, and the trailer consists of error detection and correction. And to separate two different frames, because the frames are of different size, we need a boundary to separate two frames. So each frame beginning and ending will be indicated with a separate delimiter called flag. The flag is used to indicate the beginning of a frame as well as end of the frame, and this will be separating one frame to the other. The general format of the flag which we are using is 0 followed by 6 ones followed by 0. So here you will have a flag in form of 0, 1, 1, 1, 1, 1, 1, 0. And again the flag also here will have 0, 1, 1, 1, 1, 1, 1, and 0. So we are going to have a beginning and ending indicated by a flags. Okay, I hope you people got this. We'll receive the data from the network layer. We'll add the header and trailer. And to indicate the beginning and ending of the frame, we are going to use a special characters called flag, which is 0 followed by 6 ones followed by 0. Now, there is the data which you are receiving from the upper layer. For instance, if you have some of the data which is similar to the flag. So what we are trying to do is, along with the flag, we have another special character called escape character. And if the received data is in form of flag, for instance, in between the data you are going to get 0, 1, 1, something like this. It started with 0, 0, 0, 0, and all of a sudden you have some data like 0 followed by 6 ones and 0. This is actually not the flag, it's a part of the data, but the sequence is similar to the flag. So to avoid the confusion whether it is a flag or a data, what we try to do is, whenever we have the flag or escape character content, here we are once again introducing special characters like escape. So here before this we are introducing an escape character, and again after the end of the flag we are introducing an escape character to indicate this is not the flag but it is the data. Receiver, once it finds the format again like escape followed by a flag kind of content and again escape, it will understand it's not the end of the frame, so it will remove the escape character and again try to extract the data. Okay, so when you are trying to add an extra byte to avoid the confusion from the data to the flag, we call it as byte stuffing. At the receiver, when you are trying to remove that extra character which you have added to avoid the confusion, that will be called as byte unstuffing. This is one of the very important topics, so please make sure you people remember this definition. The next kind of variable size approach is where you are going to represent the data not in form of 8 bits, but they are represented in form of bits 0 and 1s. In a bit-oriented protocol, data section of frame is sequence of bits to be interpreted by upper layer as text, audio and video so on. So here you will have the data only in form of zeros and ones. Now here there is no need of representing all the numbers or all the data in form of bytes. We can just represent them in form of zeros and ones. So data from the upper layers which is represented in form of zeros and ones, and for this we are adding a header and trailer so that the source and the destination address will be included in the header part and error detection and correction will be included in the trailer part. Now there is a probability that, and the flag is indicating the beginning and ending of the frame. So here there is again the same probability which we have discussed earlier of having a data content similar to the flag format. So when you have data content similar to the flag format, so instead of adding one extra byte like escape in the case of byte oriented stuffing or byte stuffing, here what we try to do is, when you have a data pattern similar 0 followed by 6 ones, so after 5 ones we'll add a special 0 indicating this is not the flag but it is the data. So here you could find the data format similar to the flags. So after 5 consecutive ones, we are inserting a special bit 0. At the receiver, after identifying this particular special characteristic, they will understand this is not the part of original data. It is trying to avoid us from confusing to the interpret as a flag, and we will remove those special bits which are inserted. So that we can finally extract the accurate data. So process of adding bit stuffing is a process of adding one extra 0 whenever 5 consecutive ones follow a 0 in the data, so that receiver does not mistake the pattern 0 1 1 1 1 0 for a flag. So this process called bit stuffing, and at the receiver when you remove it, you refer it as bit unstuffing. Okay, so let us make now quick understanding of the things that we have discussed as part of framing. Framing is a process of receiving the data from the network layer and adding a header and trailer, which consists of source and destination address, some control information, and error detection and correction rates. Now, the frames which can be formed can be of two forms. One is fixed size frames, where all the frames will be of uniform size, and when all the frames are of uniform size, there is no need of separate boundaries. So in the case of fixed size frames, you will not have a special characters like flags. But the second type of frames are called as variable size frames, where each frame will be of different length. Some frame will be of 1 byte, some frames will be of 2 byte size, some frames are 10 byte size. So different frames are of different sizes. So to indicate the beginning and the ending of the frame, we need to add a boundary which is called flags. To understand the variable size frames, we have two different approaches. The first approach is called bit oriented approach, character oriented approach, where all the data to be transmitted is represented in 8 bits. So that is nothing but 1 byte. So whatever the data has to be transmitted, whether it is the data to be transmitted or the error detection or correction data, or the flags we use, the header and the destination source address and the destination address, everything has to be represented in form of 8 bits. That is called character oriented approach. Now sometimes what happens is the data which has to be transmitted will be similar to the flag pattern. The flag which we are using for separating of the frames is form of zeros 0 1 1 1 1 1 0. Suppose the format is same as the flag, what we try to do is we are trying to add one special escape character to avoid the confusion. The second approach is called bit-oriented approach, where the data is represented in form of zeros and ones. So the data will be in form of bits, and there is no mandate that all the bits. So all the bits are represented in form of zeros and ones, and we are trying to use flag. We are trying to use zeros and ones, and flag will be form of 0 6 ones followed by 0. The data pattern is similar as flag. The data format is 0 followed by 6 ones. So after 5 ones, we are inserting a special 0 to avoid its confusion as flag. This is called bit stuffing. At the receiver, we will try to remove that 0, and that process will be referred as bit unstuffing. So this is one of the very important topics which you have for the exam. So make sure you understand what is framing. So in this class, we discussed about two things. The first one is how we represent cyclic redundancy check in form of polynomials. How do we implement that? What are the special set of polynomials? What are the advantages? And then we started discussing about another error detection technique called checksum. How do we implement checksum? By calculating the sum at the transmitter, transmitting at the receiver, and verifying whether they same or not. And last thing we are discussing in this class is about what do we mean by framing, types of framing, and different approaches to handle the frame. We also discussed what do we mean by byte stuffing and unstuffing, and also bit stuffing and unstuffing. The next class we'll start discussing about our next important function of data link layer called flow control. Hope we will have go through all these contents which are discussed and should come back with going through this. We'll start meet in the next class. Thank you.